Welcome to another session of our biomedical instrumentation lab. In this session, we are going to use a load cell, which is used for measuring force or weight. These are the objectives: demonstrate how to use a load cell. We're going to learn how to calibrate it, and we are going to learn how to fabricate a $1 coin counter. First of all, a load cell is a metal bar acting as a spring. It has glue strain gauges that are connected in a bridge circuit. These metal bars have holes or slits that enable a localized deformation. The strain gauges are glued very close to these holes or slits. Also, load cells have holes to attach them to a rigid structure, which we are not going to use in this session. You can find them when measuring weight, forces, or also to count vehicles. They have multiple applications. This session is replacing the hand grip session, which was based simply on a plug-and-play National Instrument sensor. It has a very similar principle. The sensor has a load cell with a black box instrumentation. I decided to replace it with a load cells where we need to build and calibrate the instrumentation. How do we calibrate the instrumentation? Well, essentially we need to generate a table of output versus input. So this means finding the system sensitivity. And then calculate the correlation of this function. Once we have that correlation, we can put that function into a microcontroller. For this exercise, my original calibrated mass resulted too low. So instead of building a weight scale like it was the logical application, I decided to build a $1 coin counter, as we are going to see. So this is the problem. Build a $1 coin counter using a 1 kilogram load cell. These are the materials: one load cell, one instrumentation amplifier, a potentiometer with 25 turns, 10 kilo ohm, National Instruments MyDAC, an Arduino with LCD and jumping cables, and there you can see what is the function of each element for this project. This is an instrumentation amplifier. Remember, the gain is set only with one resistor, which is connected between leg 1 and 8. So we need a load cell, which is going to be acting as a sensor and is in a bridge configuration. So we connected through pins 3 and 2, and the gain is determined by the potentiometer, the 20 turns 10K potentiometer connected between pin 1 and 8. Then we need to power our circuit. We use MyDAC for that purpose. MyDAC is going to power our bridge and our instrumentation amplifier with 15 volts and minus 15 volts, and also the MyDAC is providing the reference voltage, the ground, for the bridge and the instrumentation amplifier. Then the output of the instrumentation amplifier is going to be sent to my Arduino, which will have the reference same as MyDAC, and Arduino is going to send the output to a LCD display. Alright, so here we have the load cell, and here I have the mass that I was using for calibrating it. This one resulted too low for my calibration purposes, so I came up with this idea of using coins. So we have a group of coins, $1 coins, 5, 10, 15, 20, 25, and 30 in the back. So what I'm going to do is, it's very important to calibrate the load cell. The gain is set by the potentiometer that is there, sitting there. The resistor between leg 1 and leg 8 is connected through here. So I just need to move that screw to adjust the gain. To adjust it very slowly until I see an increase in. So yeah, that's it. If you see now it's saturated, it's sending 5 volts. So I need to bring it back slightly, just a bit, until I see something 4 point. Yeah, I think that's good.
So with the maximum weight that I want, which is 30 coins, I'm going to get 4.5 volts. So what I need to do is write down that value. So 30 coins equals to 4.4. So what is next is simply I need to leave the potentiometer alone. I don't have to touch it now, and simply change the weight. So I'm going to remove 5 coins. With 25 coins I get 3 point, I mean if it's moving, yeah, it may change, 3.3. With 25 I get 3.3. This is 20 coins. 20 coins I get 2.2 volts. 15 coins 15 coins 1.1, I guess, hard to tell. 10 coins 10 coins is equal to 2.07, yeah. Yeah, 5 coins is 5 coins is essentially 0, so not able to differentiate. Alright, so this is very important. Remember, we want to get the transfer function, so it's essentially output over input. So our output is voltage, and the input is going to be coins. So I obtained 4.4 for 30 coins. I obtained 3.3 for 25. I obtained 2.2 for 20. 1.1 for 15. 0.07 for 10 coins. And really this is not reliable, but I'm gonna put it anyway. 0.45. Then I'm simply going to plot this and extract the correlation. So you can see this is not consistent with all the measurements, so I'm simply going to not include it in the plot. The most important thing of this procedure is that extract the correlation. So we select the data and then add trend line. Excel is going to plot calculate a linear correlation. So display it in the and let's display the equation in the. So what I need to do is put this equation in my Arduino. .6033 times voltage is going to give me plus 9.8. And then I'm going to display this variable into the LCD. So here I'm indicating, put the cursor in this location and print the value there. So let's upload it and see what we get. Alright, so this is when the program is uploaded. You can see that apparently it's working properly, because with 0 volts, I have 10 coins, which is essentially where the linear function is located at the y-axis. So I have here 20 coins, 1, 2, 3, 4 packages of 5. And you can see, it's counting at this correctly. So I'm going to, play with it. Gonna put 5 more. Hopefully, you can see
is giving the correct amount. So yeah, I have 25. I don't know if it will detect another coin. Yeah, 26 correctly. 27. And then I have another one, 28. So that's how a load cell works.